Hello students, let us continue chapter 10 Gravitation. Today we are going to discuss our next topic, free fall and motion of the objects under the influence of gravitational force of the earth. So before that, let's start with the example. Example number 10.1. The mass of the earth is 6 into 10 to the power 24 kg and that of the moon is 7.4 into 10 to the power 22 kgs. If the distance between the earth and the moon is 3.84 into 10 to the power 5 kilometer, then calculate the force exerted by the earth on the moon. And here the G, that is gravitational constant, is given 6.7 into 10 to the power minus 11 Newton meter square per kg square. So let us start the solution. Here what we have given, the mass of the earth, capital M, it is given 6 into 10 to the power 24 kgs, and mass of the moon, small m, is 7.4 into 10 to the power 22 kgs, and the distance between the earth and the moon, that is D, is equal to, between the earth and the moon, that is D, is equal to 3.84 into 10 to the power 5 kilometer, or we can say 3.84 into 10 to the power 5 into 1000 meter, because we have to convert kilometer into meters for the standard relationship. 3.84 into 10 to the power 5 into 10 to the power 3, that is 10 to the power 8. 3.84 into 10 to the power 8 meters, and G is given 6.7 into 10 to the power minus 11 Newton meter square plus kg by kg square. So we have discussed the equation in our last video, that is F is equal to G m1 m2 upon d square, or capital M into small m upon d square. That is the force exerted by the earth on the moon. And putting the values, that is 6.7 into 10 to the power minus 11 Newton meter square per kg square into 6 into 10 to the power 24 kg into 7.4 into 10 to the power 22 kg divided by d square, that is 3.84 into 10 to the power 8 meters whole square. And it gives the answer 2.01 into 10 to the power 20 Newton. Thus we can say the force exerted by the earth on the moon is 2.01 into 10 to the power 20 Newtons. Now free fall. To understand this concept, let us have an activity 10.2. Take a stone, throw it upwards. It reaches a certain height and then it starts falling down. Why? Let us discuss this in deep. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of falling objects? Yes. While falling, there is no change in the direction of motion of the object, but due to the earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. We know that we have discussed this in chapter number 8. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force, and therefore this acceleration is known as the acceleration due to gravitational force of the earth, or acceleration due to gravity. Now it is denoted by small g, and the unit of g is the same as that of acceleration, that is meter per second square. Now we know that from the second law of motion that force is the product of mass and acceleration. We have discussed this in last chapter. Let the mass of the stone in this activity 10.2 be small m. We already know that there is acceleration involved in falling objects due to the gravitational force and is denoted by small g. Therefore, the magnitude of the gravitational force F, that is capital F, will be equal to the product of mass and acceleration due to gravity. So we can write F is equal to m into g, mass into acceleration due to gravity, small g. And from the equations we will have we have discussed the equation in last video, that is F is equal to G m upon d square. In place of F, we can put mg. Mg is equal to g m into m upon d square, where capital M is the mass of earth and small m is the mass of object, upon distance or square of distance between them, that is d square. Or we can write on cutting the m and m, on solving it, we will have the relation small g is equal to capital G, that is gravitational constant, into capital M upon d square, and where m is the mass of the earth and d is the distance between the object and the earth. Let an object be on or near the surface of the earth. The distance d will be equal to r. R will be the radius of the earth, capital R. Thus, for objects on or near the surface of the earth, we can write the formula mg is equal to g, that is capital G, gravitation constant, capital M into small m upon r square, instead of writing d square. And on solving this, small n and small m will cut out, and hence we will have g, small g, gravitational acceleration due to gravity is equal to g m upon r square. The earth is not a perfect square. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most calculations, we take small g to be more or less constant on or near the earth. But for objects far from the earth, the acceleration due to gravitational force of the earth is given by the equation g, that is g m, capital G m upon d square. That is our first equation. Now to calculate the value of g, that is acceleration due to gravity, small g. To calculate the value of g, we should put the values of capital G, that is gravitational constant, capital M, mass of earth, and radius of the earth. So namely universal gravitational constant, that is g. The value is 6.7 into 10 to the power minus 11 Newton meter square per kg square. Mass of the earth, capital M, is 6 into 10 to the power 24 kgs, and radius of the earth, capital R, is equal to 6.4 into 10 to the power 6 meter. On putting all the respective values in the formula, small g is equal to capital G m upon r square. We will have 6.7 into 10 to the power minus 11 into 6 into 10 to the power 24 divided by 6.4 into 10 to the power 6 square. On solving this, we will have the value, the answer, 9.8 meter per second square. Thus, the value of acceleration due to gravity of the earth, that is g, is equal to 9.8 meter per second square. Now, motion of the objects under the influence of gravitational force of the earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from the height at the same rate. To discuss this, let us have an activity 10.3. Take a sheet of paper and stone. Drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We see that paper reaches the ground little later than the stone. This happens because of air resistance. The air offers resistance due to the friction to the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. Then we know that an object experiences acceleration during free fall. This acceleration experienced by an object is independent of its mass. We have discussed in the equation. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of the Leaning Tower, Pisa, in Italy, to prove the same. As g, that is acceleration due to gravity, is constant near the earth, all the equations for the uniformly accelerated motion of objects become valid with the acceleration A replaced by g, small g. So the equation we have v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus twice as. We have discussed all the three equations in chapter number 8, where u and v are the initial and final velocities and s is the distance covered in the time t. So in applying these equations, we will take acceleration a to be positive when it is in the direction of the velocity, that is in the direction of motion, and the acceleration a will be taken as negative when it opposes the motion. And same thing we will consider in acceleration due to gravity g. Now example 10.2. A car falls off a ledge and drops to the ground in 0.5 seconds. So let here the acceleration due to gravity, that is small g, is equal to 10 meter per second square for simplifying the calculations. And we have to find out three things. The very first, what is its speed on striking the ground? What is its second? What is its average speed during 0.5 second? And the third one, how high is the ledge from the ground? So let us start the solution. What we have given? Time t is given, t is equal to half second, 0.5 seconds. Then initial velocity, that is u, will be 0 because car falls off. So the initial velocity will be 0 and then falling gets started. So it will be 0 meter per second. And acceleration due to gravity, that is small g, is given 10 meter per second square. And acceleration of the car will be here, acceleration A will be 10 plus 10 meter per second square, as it is going downwards. That's why on going downward towards the earth, the acceleration will be positive because it is in the direction of motion, direction of the speed. So let us start the first point. What is its speed on striking the ground? The speed will be v is equal to u plus a, v is equal to u plus at, where u is 0 here, initial velocity is 0. Or we can write v is equal to at, where a is 10 meter per second square and t is 0.5 second. On multiplying 10 into 0.5, we will get 5. And on solving meter per second square into second, we'll get answer 5 meter per second, because second square and second will get cancelled out. The second point, what is its average speed during the 0.5 second? We know that what is average speed? Average speed is initial velocity plus final velocity divided by 2. Here u is 0 and v is 5 meter per second. So we will write 0 plus 5 divided by 2, where 2.5 is the answer. 2.5 meter per second. And the last one is distance travelled. Distance travel, the second law of equation, second equation of motion, s is equal to ut plus half at square. So we can write half into u is 0, half at square will be half into 10 meter per second square into 0.5 second whole square, because t square. And on solving we will get 1.25 meter. So speed on striking will be 5 meter per second. Its average speed during the 0.5 second will be 2.5 meter per second, and height of the ledge from the ground, that is distance travel, will be 1.25 meter. So students, I hope you understood the topic of free fall and numerical regarding it. Thank you for listening.